Welcome to Lecture 3.5 on polynomial functions for Math 1324. Continuing along with letting you see a little bit of insight into your professor. This is an interesting trip that I took back in 2003 with my two young sons at that time. And we did a house swap in Northern Ireland. And that's where a family from Ireland and we agreed to have vacations at the same time. And we went and lived in their home while they came to Dallas and lived in our home. We also agreed to swap cars. And so this was a great way to take an adventure for a very inexpensive money. We were there for about a month. And you can imagine what a hotel or rental car would have cost for that period of time. And so here we had I think a 3 or 4 bedroom home. They had children about the same age. They even had a PlayStation or something like that, which of course my sons loved. And it was just a great way to experience another culture by living in a neighborhood and being able to explore. So I just want to give you that insight that adventures don't always cost a lot of money. If you can be creative, there are ways around it. And stepping outside of your world, stepping into another land, another culture, can be a very powerful and transformative experience. In addition, I'm going to try something else today. I'm going to take a brief pause before we begin and just share something different. I think of this kind of like clearing the history in your computer and just kind of taking a break and looking at something different that may touch you in a different way instead of a direct way like mathematics. This is a poem by Mary Oliver. I've loved this poem, and different stanzas of this poem really speak to me. So just listen to it, and if it speaks to you, great. And if not, that's fine too.
So this is Wild Geese. You do not have to be good. You do not have to walk on your knees for 100 miles through the desert repenting. You only have to let the soft animal of your body love what it loves. Tell me about despair, yours, and I will tell you mine. Meanwhile, the world goes on. Meanwhile, the sun and the clear pebbles of the rain are moving across the landscapes, over the prairies and the deep trees, the mountains and the rivers. Meanwhile, the wild geese high in the clean blue air are heading home again. Whoever you are, no matter how lonely, the world offers itself to your imagination, calls to you like the wild geese, harsh and exciting, over and over, announcing your place in the family of things.
So let's begin with our lecture. We're looking at polynomial functions, and we say a polynomial function of degree n is a function whose rule is given by a polynomial of degree n. Don't you love math sometimes? Sometimes it's just stating the obvious, and sometimes it's confusing as hell, the rules and the way that we state them. So this is a really simple concept. The degree of a polynomial is equal to the largest exponent when the polynomial is written in standard form. All three of these examples are written in standard form. And what that means is that you see terms that are added or subtracted, 3x squared plus 4x minus 6, etc. A polynomial can also be in factored form. This is when you factor something and you have like x plus 2 times x minus 3. Okay? So that's a different way. You're going to have to use a different method to find the degree there. But when it's in standard form, it's simply the largest exponent on the x, or the variable. Okay? All three of these are written in correct standard form, which goes from the largest exponent to the smallest. If the polynomial is written in this form, then it's even easier to find the degree because it will be in the first term, which it is for all three of these. Okay? For f of x, we're looking for the exponent that appears on the x term. We do not see an exponent, so be careful. When you do not see an exponent, the exponent is 1. Okay? So this is a polynomial of degree 1. The second polynomial, g of x, is a polynomial of degree 2 because we have the largest exponent is a 2. And h of x is a polynomial of degree 4 because the 4 is the largest exponent. If we had another function, let's say I of x, which just equaled the number 2, this is a degree 0. Constants are a degree 0. Because we could write, for example, in f of x, we could write the second term instead of just minus 2, we could write it as minus 2 times x to the power of 0. Because remember, anything that's to the power of 0 is equal to 1. And so constants are a degree 0. Now, why do we care about this? Because polynomials exhibit some consistent graphing shapes. So let's look at a couple of graphs. When we're graphing a polynomial with a degree higher than 1, we've already graphed degree 1s. Those were all our linear equations. When we're looking to graph polynomials with degrees higher than 1, we want to consider x values on both sides of the y-axis, positive and negative x values. So for this polynomial, in example 1, we have a degree 3. We have a function that begins down low and ends going upward. In example 2, again, we have a polynomial with a degree greater than 1. This is a degree 4. Then we're going to look at positive and negative x values again and calculate the y values or the f of x values. Remember that y and f of x are the same thing. And here we have a graph that begins and ends in the same direction. In this case, it goes up on both sides. So we're going to look at what are the impacts, what do we look at and find out these consistent graph shapes, okay? What we're going to look at, one of the things that we're going to look at is whether the degree is odd, as in example 1. And notice that the odd polynomial begins and ends in the opposite direction. Odd, opposite. Begins down, ends up. Begins down, ends up. Odd polynomials begin and end in the opposite direction. Even polynomials, as in graph example 2, begin and end in the same direction. Odd, opposite, even, same. So we've already looked at one of those characteristics, whether the degree is odd or even. What's the other impact? The other impact is whether the coefficient in front of the leading term or the term with the largest exponent, whether it is positive or negative. Okay, and you can see the A here. We're looking for the term, the coefficient, the number, the constant that is in front of the x term with the largest exponent. And then just as I said in the last slide, we're looking at whether the degree of the polynomial is odd or even. Notice here, a is equal to 4 and it is positive. The degree is 3, so it is odd. So we have a positive odd polynomial. The degree is 5, so it is odd. That is the largest exponent. A is equal to negative 2, so it is negative. So we have a negative odd polynomial. Here we have 1/3 x squared plus 4x. The degree is 2, which is even, and a, the coefficient, is 1/3 or positive. We have a positive even polynomial. And this last one we have negative x to the 8th. The number in front is negative 1 times x to the 8th. The degree is 8, so it is even. A is negative 1, it is negative, and so we have a negative even polynomial. When a polynomial is positive and odd, it goes up. It goes down, it starts in the bottom left and ends in the upper right. This is a graph I call an S-up. When a polynomial is negative and odd, it starts up and goes down. This is kind of intuitive. Positive things go up, negative things go down. This works throughout all four quadrants here of these different polynomial shapes. When we have an even positive polynomial, we get a smile. A lot of students call these smiles, like we had with the parabola. Positive things make us smile, but an even positive polynomial starts upward and ends upward. Negative even polynomials are a frown. Negative things make us frown. Starts down and ends down. Again, it's important to see here that odd polynomials begin and end on the opposite side. Even polynomials begin and end on the same side, and they kind of work intuitively with positive or negative. Positive things go up, negative things go down. So let's get a few more pieces of information and then do some problems. When we're talking about the number of peaks and valleys, in this graph up to the right, you see one valley here around -1, and a peak somewhere around, looks like about a 1/2. It's hard to see those numbers, they're pretty small. The number of peaks and valleys that a polynomial function can have is 1 less than the degree. So for example, if this was a degree 3 polynomial, it could have at most 2 peaks and valleys. The number of x-intercepts, remember an x-intercept is where the graph crosses the x-axis, and we have 3 of those. We have one at -2, we have one at 0, and we have one at +1, using all x values. The maximum number of possible x-intercepts is equal to the degree, so the number of x-intercepts is equal to or less than whatever the degree function is. Okay, some more data, but let's look at an example. And then I want you to pause this recording and see if you can do the other 3. So the first one, f of x equals x cubed minus 4x plus 2. We're trying to figure out what the degree is, what's the maximum number of peaks and valleys, and what is the maximum number of x-intercepts. The largest exponent is a 3, so this is a degree 3. The number of peaks and valleys, maxes and minimums, is 1 less for maximum, so at maximum it could have 2. The maximum number of x-intercepts is the same as the degree, so this would be the max number of x-intercepts would be 3. Go ahead and pause the video and see if you can do the other 3 examples. I'm going to move through these others pretty quickly. The second equation or function is f of x equals x to the 5th minus 5x cubed plus 4x. The largest exponent is a 5, so it's a degree 5. 1 less for the maxes and minimums or peaks and valleys is 4, and the maximum number of x-intercepts is 5. In the third equation, 1.5x to the 4th plus x cubed minus 4x squared minus 3x plus 4. The largest exponent is a 4, so this is the degree. The maximum number of peaks and valleys is 3, and the maximum number of x-intercepts is 4. This one actually only has 2, and that's the number you see there as well. So it doesn't have to have the maximum number, but that is the maximum it can have. In the last example given, we have the degree is 6. The function is f of x equals negative x to the 6th plus x to the 5th plus 2x to the 4th plus 1. The largest exponent was 6, so this is the degree. The maximum number of peaks and valleys, which is not shown here, should have been 5. It actually only has 3. Okay? The maximum peaks and valleys for this fourth example is 5, although it only has 3. I wanted to show you these examples because sometimes students get confused that they think it has to have the same number. And again, in the last example, the maximum number of x-intercepts is 6, but the actual graph only has 2. I want to show you one more example because this can be kind of tricky, and I want you to do the same thing, answer those 3 questions. So if we had f of x equals 4x squared plus 2x minus 3x to the 4th minus 15, what is the degree? Now you may have gotten a little lazy and gotten used to a pattern and just used the exponent on the first term, which is 2. But if you look further in, this is not in proper standard form. The largest exponent term is actually the third one in. The largest exponent on x is a 4. So this is a degree 4. The maximum number of peaks and valleys would be 1 less or 3. And the maximum number of x-intercepts would be 4. I just wanted to show you one that wasn't in proper order, so you need to look at all of the terms in a standard polynomial. Okay? Let's try another one. So we have this graph up here. What do you think it's possible that the degree could be? Think about the shape and what we learned about the shapes. This starts up and ends down. And then think about the number of x-intercepts on here, or the number of peaks and valleys. Okay? And based upon n equaling, or the degree, or n equaling 2, 3, 4, 5, 6, or 7, which of those are possible? Well, first off, we have a graph that's beginning up and ending in the opposite direction, going down. What do we know about the degree when it starts and ends in opposite directions? It has to be odd. Hey, they both begin with the letter O. So we automatically know that 2, 4, and 6 are not possible. Okay? If we look at the number of x-intercepts, we have 1, 2, 3. So this could be a degree 3. The number of x-intercepts has to be less than or equal to the degree, so this could also be a degree 5, or it could also be a degree 7. So the 3 possible degrees here are 3, 5, or 7. These are the actual graphs for the 4 problems we did in the last problem. Okay? If you remember, C and D did not have as many x-intercepts as they could have, and you can see here in C that the graph kind of has peaks and valleys that never cross the axis. The same thing here in graph D. Although it goes up and has a peak and comes back down, it doesn't go back across the x-axis. Okay? It's important that you know all of these things about degrees. It's important that you know about peaks and valleys, the number of x-intercepts, and now we're going to look at some more things to help us graph. When you have a polynomial function, it's a smooth, unbroken curve that goes forever on the left and the right. This means it is the domain of a polynomial is all numbers. There's no holes, there's no breaks, etc. Okay? At the outer edges of the x-axis towards the arrow, the graph resembles the graph of its highest degree term. And that's why they begin and end if they're even on the same side, or begin and end on opposite sides. We're talking about at the outer edges of the graph. Okay? So example C says, let g of x equal x cubed minus 11x squared minus 32x plus 24. Is this a complete graph of g of x? That is, does it show all the important features of the graph? Well, let's think about that. We have a degree 3 polynomial, so we know because it's degree 3 and our a, the number in front, is a positive 1, we have a positive odd polynomial. Well, odd polynomials should begin and end in the opposite direction, and this one does not. In fact, it should start down low and go up. Remember, odd positives increase over the graph. They start low and end up. So this is not the complete graph. Now, why is that? Well, look at our axis. We're only graphing it from x equals, looks like 4 to x equals negative 4. So there's probably a bigger graph, a bigger window. On your calculator, it's called a window. It's the second button at the top. And you can establish like the upper and lower values of y, the upper and lower values of x, and then the interval, like here this is an interval of x of 2, and it looks like the interval for y is 20, the delta or the triangle. So you can change that on your calculator. And here we have a graph from a calculator, and here they set y maximum is 3, y minimum is negative 700, and the units is 100. Here they set the x minimum is negative 7, the x maximum is 15, and the unit is 1. Try to graph this in your calculator if you don't have practice at graphing, and see if you come up with this same graph. And now we can see a shape that is correct for a positive odd polynomial. Again, try to change the window in your calculator. This is really good practice if you're not familiar with graphing, and then move forward. Another concept about polynomials which really helps us graph is something called multiplicity. And multiplicity is a number that represents the number of times a factor occurs, a root factor. Or you could say the number of times an x-intercept or a zero of a function occurs. Okay? So this is a polynomial in factored form, different than in standard form. We'd have to multiply this out using FOIL and then using higher order polynomial distribution processes. I usually use a multiplication table with boxes to figure this out. But notice we have 3 root factors, x plus 2, x minus 1, and x minus 3. If we wanted to find the zeros of the function, we would set each of these factors to 0, equal to 0, and solve. Okay? So we have x-intercepts, or zeros of a function. X plus 2 equals 0 gives us x equals negative 2. If we notice there's a square on this, which means this factor occurs twice, x plus 2 times x plus 2. So that's why the multiplicity is 2. The multiplicity is the number of times a factor occurs. And if it's in exponential form, it is the exponent. X minus 1, no exponent, or really an exponent of 1, occurs 1 time. If we set x minus 1 equal to 0, we get x equals 1. So we have an x-intercept, or 0, at 1. We have an x-intercept at x equals negative 2. And we have an x-intercept for the last factor at x equals 3. Okay? Both the zeros at 1 and 3 occur 1 time, those factors, so their multiplicity is 1. You'll notice that I've added terms even or odd, and that's what we really care about with multiplicity. Okay? Just like an even polynomial begins and ends at the same place, when you have even multiplicity, when you hit that x-intercept, you bounce back. You do not cross over into the other side of the x-axis. It bounces back. If you have odd multiplicity, it begins and ends on the opposite sides, you would go ahead and cross through that x-intercept. So let's look at an example here. Find x-intercepts, the multiplicity, and the graph of x to the fourth, x plus 3 squared, and x minus 3 cubed. Okay, we have three factors. We have x to the fourth. If we set that equal to 0, we get x equals 0, and a multiplicity of 4. X plus 3, if we set that equal to 0, we get negative 3 is the 0, and a multiplicity of 2. X minus 3 equals 0, we get x equals 3, and a multiplicity of 3. Okay, setting each of those factors equal to 0, we get x equals 0, x equals negative 3, or x equals positive 3. And then we can see the multiplicity by the exponent. At 0 it is even, at negative 3 it is even, and at positive 3 it is odd. Okay, so let's walk through this. At negative, oh, that should have come up earlier. Here is the graph of our original one. Notice that it is even at negative 2, and remember, evens stay on the same side, so it touches and bounces back, touches and bounces back. We have odd zeros at 1 and 3, so we cross over, and then we cross back over. Okay, even multiplicity bounces back in the same direction. Odd crosses over, odd crosses over. Even bounces back. So when we're graphing these polynomials, we're going to use some of the information, and I'm going to take you through a step-by-step process for graphing. So the first thing we want to do is to find the degree and the general shape. Now we have a bit of an issue here because every other polynomial that we found the degree was written in standard form. But this polynomial is written in factored form. Okay, we'd have to multiply it all the way out to get it in standard form, but we really don't need to do that. What we can do is we can look at each of the x terms, or the first terms in each factor, if you will. If we do that, we see we have a 2x, we have an x, and another x. If we multiply those, we get 2x cubed. Now it's important to pay attention to not only the numbers in front, but if they're positive or negative, and then if there is an exponent on the outside of the parenthesis, to take that first term and apply that exponent on the outside. So for example, if the first term was 2x plus 3 squared, then we'd have 2x in parentheses squared, which would give us 4x squared times x times x. Okay, that's really important, especially when one of these x values, the a in front, is a negative, so that we find out the final term whether it's positive or negative. So here we have a positive odd polynomial, so we expect our general shape to be that S up. It'll start down low on the left and end up high on the right. The next thing we're going to do is to find all the x-intercepts and the multiplicity of each of those. And that's where this form of the polynomial in factored form makes this easier, because we can just set each of the factors equal to 0. Okay, the x-intercept is when y equals 0 or f of x equals 0. So we set the entire equation equal to 0. And this will be true if any of the factors is equal to 0. If we set 2x plus 3 equal to 0 and solve, we get x equals negative 3 halves. If we set x minus 1 is equal to 0, we get x equals 1. If we set x plus 2 equals 0, we get x equals negative 2. Okay? So we have three different zeros here, or three x-intercepts. Now what is the multiplicity on each? Again, we go back and look at the exponent on the parenthesis, and it's 1 on each of those, so the multiplicity is 1 for every single factor. Remember, an odd multiplicity begins and ends on opposite sides, so these are the ones that will cross over the x-axis. The next thing we're going to do is find the y-intercept. Where does the function cross the y-axis? Remember, y-intercepts are found by making the x equal to 0. Okay, if we do that, we get 3 times -1 times +2, or -6. The last thing we might want to do, we can look at these and plot these points and know what's happening at each of the intercepts, know what's happening with the general shape, but we also might want to find some additional points. And you can do this by putting the equation into your calculator, y equals this function, and then looking at the table function. So you don't have to calculate them all, or you can. And so here's our graph. We have zeros at -3/2, +1, and -2. We know that our graph starts down in the left and ends up in the right because it's positive odd. We know that it crosses at y. So we start down here, cross over, hit -6, and cross over again. And so the multiplicity and the degree and polarity of the lead term really helps us facilitate graphing in a good way. Okay, so it's a good idea to remember this chart and these steps to find, and hopefully this will help you finish out. I hope you enjoyed that poem. Maybe listen to it again. I think there's some great stanzas in that about just letting your body love what it loves. Anyway, good luck on this. Reach out as you need help.